All right, so there are many research directions in flow matching. By the way, there is an intersection of flow matching and diffusion, which is all about everything about stochastic flow matching, or also it is also related to uh, Schrödinger bridge, this Schrödinger bridge, and for example, if you write the reverse SDE, you will see a term that let me speak like this: if there is no noise in your velocity, so if dx by dt is u, then you will have a flow matching, and you have a continuity equation. This continuity divergence of p probability times your velocity. But if there is noise, I mean dx is equal to f drift times dt plus g dw. If there is a noise term, then your probability is just a Fokker-Planck, which is minus divergence of pu plus something like epsilon Laplacian of p. So when epsilon is 0, then it's the original. It's also related to that regularized optimal transport approach to flow matching. So they are very interesting. But there is also connection with flow matching has connection with variational approaches, variational inference approaches, and you will see our latent variable here could be x1, or could be very sophisticated things like the coupling of x0 and x1. This could be a very nice latent variable, which I haven't seen in paper. So you can write a paper with this kind of latent variable. So this NeurIPS paper in 2024 is very important. By the way, this AM lab is very important. Also, this UVA Bosch Delta lab is very important lab. They have very good articles. So the key observation of variational flow matching is that we can parameterize the vector field of the flow in terms of variational approximation of the posterior probability path, which is a distribution over possible endpoints of a trajectory. So, from flow matching, you can set this flow as this. It's then the typical flow matching objective that you see in original papers is expectation of you want to regress the true with this neural network. This is a velocity field. You want to regress it. But then it is also, because the straightforward is not possible, if you condition on that, it's tractable. This is conditional flow matching objective. But then the researchers noticed that we can rewrite everything. We can, just like variational autoencoder, that is a Z latent variable. Now here you can condition on your latent variable could be x1. So again, if you rewrite the equations, you will see this term again. This KL divergence between these are interesting. That are the loss that we call variational flow matching. So we do not seem to obtain much from this variational view due to intractability of x1 condition on x. So we can simplify the objective under the typical case where the condition of vector field is linear, such as a straight line interpolation commonly used in flow matching. First, we notice that the expected value of linear conditional velocity fields simply equals the conditional velocity field toward the expectation, and they proved it. So, without loss of generality, we can just consider this fully factorized approximation. Then you will notice that this is the mean field variational flow matching. So it will be reduced to this log of Q. So this multiplications become summation over d different dimensions. And to calculate the vector field, we can simply substitute the factorized distribution into equation 8. If you put it here, if you put the factorization of that, then you will see, however, this still requires an elevation of expectation. Fortunately, leveraging the linearity condition significantly simplifies this computation, since as long as we have access to the first moment of one-dimensional distribution, we can efficiently calculate V by simply considering the conditional field towards it. So if we now use the standard flow matching case of using a conditional vector field based on linear interpolation, the approximate vector field can be expressed in terms of the first moment of variational approximation. And this is the parametrization of vector field in cat flow. So this paper introduces cat flow, categorical flow. So given an interpolant, this is a kind of a stochastic interpolant, and cat flow predicts a categorical distribution, parameterized by a vector mu. So in cat flow, we directly apply variation flow matching framework to the categorical case. So we parameterize it like this, and then the this component of the learned vector field looks like this. So it learns a distribution over conditional trajectories to all corners of that probability simplex that I showed you. Now, the mean field variational flow matching, this one, can be written out explicitly. Writing out the probability mass using this, and then we find that cat flow is given by the cross entropy loss. So we can actually compute VT. This can be done efficiently because of this relation. So they discovered, they saw the relationship to flow matching that admits flow matching as a special case under certain assumptions when variation approximation is Gaussian. So this is a very beautiful observation. This remark is interesting. So assume the conditional vector field is of this linear form, and A and B look like this, then variation of flow matching reduces to flow matching. Of course, this A is an invertible matrix, and BT is a function like this. Also, it has relationship to score-based models that you can parameterize the score as an expectation with respect to variational approximation Q. So it's like approximation of the score is the score. Expectation of score is the score. So it's very natural thing that they develop in their paper, very interesting observation. So we can construct stochastic generative dynamics to approximate the true dynamics. We will rewrite the variational flow as expectation of log of Q. Then the theorem says that there is an upper bound to log of expectation of log of Q1, which is this one. And the nature of this is lambda is just the non-negative function, and C is a constant. So the upper bound it depends on your loss, the loss that expectation of log of Qt. So these QM9 and zinc, of course, PyTorch gives just a fraction of that. You see these for many generative graph modeling approaches. There are many measures like validation, uniqueness, FCD. This means lower is better. Uniqueness up, higher is better. Validation should be higher. And they compare it with cat flow. For example, if you remember, I talked about digress in the playlist for diffusion. You see some improvement for validation. Or for uniqueness, now uniqueness is a little bit better. So these are molecules generated by cat flow. Let me talk about limitation. While the variational flow formulation that we identify has potential in terms of its generality, we have as yet only considered its application to a specific task of categorical graph generation. We leave other use cases to future work. A limitation, which is shared, is that reasoning about a set of possible edges has a cost that is quadratic in the number of nodes. As a result, cat flow does not scale well to, for example, large proteins of 10,000 or more atoms.